Okay, so we've defined temperature. Temperature is a measure of average kinetic energy per particle. Okay, so let me actually go to the whiteboard for a second. So here's an interesting fact. Okay, so here, let's say here's the table in your room, and here's the air in your room. Okay, now this is at the same temperature. Presumably this is, okay. Now in thermodynamics, we'll always deal with temperatures on the Kelvin scale. So let's say this is at 300 degree Kelvin. This is also at 300 degree Kelvin. What that means is the average kinetic energy of these air molecules, again, they have different masses, is equal to the average kinetic energy of the molecules in the table. These molecules are vibrating like that, okay? And their average kinetic energy is equal to the average kinetic energy of the air molecules, okay? So if two objects are at the same temperature, the average kinetic energy per molecule are equal. So that's what temperature tells you. Okay. Now we'll talk about the scales on which the scales we use to measure temperature. So three commonly used scales are Celsius, Fahrenheit, and Kelvin scale. Okay. It turns out that in principle you can make any number of temperature scales. So you can make an infinite number of scales, but these are the three commonly used. Okay. Now to define a temperature scale, what needs to happen, what you need is two phenomena. So here's the ice point and steam point. What this is telling you is, this is, we've experienced, well, so this is from experience, what we find is that water freezes at the same temperature, okay? So that's at 1 atmospheric pressure. And if you freeze water today at 1 atmospheric pressure and freeze it tomorrow in the morning, 10 years from now, you find that it freezes at the same temperature. Similarly, water boils at the same temperature at a pressure of 1 atmosphere. At different pressures, it boils at different temperatures, but at 1 atmosphere, it boils at the same temperature. Okay. So now to make a scale, all you do is call this phenomenon occurring at some temperature, any number you want to call it. On the Celsius scale, they call it 0 degrees Celsius. On the Celsius scale, they call the boiling temperature of water as 100 degrees Celsius. So if you want to make your own scale, you can call this 50 and that thing 500, whatever, okay? So to make a scale, you assign a value to this phenomenon and this phenomenon. The Fahrenheit people call the freezing point of water 32 degrees Fahrenheit, and the boiling point of water 212 degrees Fahrenheit. The Kelvin scale, this 273 degree Kelvin, and that's 373 degree Kelvin. Okay, so here's something to notice. On the Kelvin scale, the number of degrees between these two phenomena are 100 degrees, and there's 100 degrees between these two phenomena. So the question is, why have these two scales? So here was the problem. Okay, on this scale, okay, so the Kelvin scale came about now. Okay, so we saw that temperature measures the average kinetic energy per molecule. And the next natural question is, so what is the lowest temperature you can reach? And once we realize that the best you can do is you can stop all the molecules, okay? And once all the molecules have stopped, then you reach the lowest temperature. And you want to call that 0 degree Kelvin. And that's how come the Kelvin scale was born. Okay, so the Celsius scale was designed before we realized that. Okay, so on the Celsius scale, the lowest temperature would correspond to minus 273 degrees Celsius. And that's an odd temperature to have. So the Kelvin scale is just the Celsius scale rescaled. Okay, so that's how come, so they're related like that. And of course, the Fahrenheit scale, this is a good temperature scale to measure body temperature and all. You see, there's 180 degrees between these 2 points. So this is a finer scale than that. Okay. Anyway, so to summarize again, to build a temperature scale, what you need is 2 physical phenomena that happen, well, so physical phenomena occur at the, that occur at the same temperature. And then you call at the higher temperature. Okay. So in principle, you can build an infinite number of scales. All right, so these are 2 phenomena. They're dependent on the pressure and so on. So for today, for technical reasons, we use 2 other phenomena. So absolute zero, that's very precisely defined. And the triple point of water, which is another more precisely defined point. So these are 2 phenomena that we use to define the temperatures. Okay, so absolute zero, now you understand what that means when all molecular motion ceases. The triple point of water is, let's show you the triple point of water. Okay, so here's the triple point of water. Here, we'll talk about this phase diagram more. The phase diagram says here, what it does is, this is for water, a H2O. This is plotting H2O at various pressures and temperatures. Okay, so what this diagram is telling you is, at 1 atmospheric pressure below 0 degrees Celsius, H2O can only exist in solid phase. That's what this diagram tells you. At 1 atmosphere above 0 degrees Celsius, it can only exist in the liquid phase, okay? And so on. That's what this diagram is telling you. So you see here, this point corresponds to where all phases are coexisting. So this line tells you, this line shows you where they can coexist. The solid and water and liquid phase can coexist. This line tells you where the water and gas phase can coexist. Okay. And this line, this phase diagram is an equilibrium, okay, an equilibrium phase diagram. So this tells you the triple point where at this temperature and this pressure, so that is 6,000th of an atmosphere, so very low pressure. At this temperature and this pressure, all 3 phases can coexist. And that's what this diagram is showing you. See, here the vapor phase, liquid phase, and solid phase of water. Okay. And the triple point is, see, if you increase the temperature and the pressure, all this stuff would become water. If you decrease the temperature, so from this triple point, you could go into any phase. Okay. So that's the triple point of water. And those are the points that are used to define temperature scales today. You saw absolute zero. So what this diagram is showing you is 3 gases taken. So if you take different amounts of gases in 3 containers, and they will be at different pressures, and as you decrease their temperature, the pressure falls, which is what you saw. Okay, as you decrease the temperature, the pressure is falling. So watch that, and the pressure will fall. The pressure arises because of the air molecules bouncing off the walls. Okay? And if you slow down the molecules, they're bouncing off the walls slower, and the pressure decreases. Okay, so this is how absolute zero was discovered. And as you decrease the temperature, the pressure falls, and you'll see that all these 3 meet at the same point at minus 273 degrees Celsius. Okay, that's when all molecules have stopped, and that's the absolute zero. So here's the phase diagram. So this, you have phase diagram. Phase diagrams are very important. That show what phase that particular substance will be at various thermodynamic variables. So you can use any two thermodynamic variables. Here's the common one: pressure versus temperature. Okay, so this tells you below. So this is 1 atmosphere, and by the way, the scale is non-linear. Okay, so you can see that the scale is non-linear. These lines are coexistence lines. So at these temperature and pressures along these lines, both ice and water can exist. In this area, only ice can exist. In this area, only water can exist. In this area, only water vapor can exist, and so on. Okay. So at 1 atmosphere, so this is the coexistence phase, water boils at 100 degrees Celsius. Okay. At lower pressures, so if you go up on top of a mountain or something, water will boil at a lower temperature. Okay. So if you cook pasta on top of a mountain, it doesn't cook too well. Okay. On the other hand, if you increase the pressure, water would boil at a higher temperature. Okay. And you could cook stuff faster. All right. Anyway, so the phase diagram is extremely important. The phase diagram of water is unusual because the melting curve has a negative slope. What they're telling you is this thing. The melting curve, this is the melting curve, has a negative slope. You would think that, so let's go to a whiteboard. Okay, so if you had some substance, you think that if you applied pressure, on the object, the higher the pressure, the harder it would be to melt it. Okay, so you think that the melting curve should have a positive slope. As the pressure increased, the melting curve, the temperature should increase. As the pressure increased, it would be harder to melt it. But water, you saw that from water, instead of being positive, the slope is negative. Okay. Now, so thanks to this curve, so here's the phase diagram for water, pressure, temperature, and here's 1 atmosphere. Let's go. Yeah, here's 1 atmosphere, and there's roughly 0 degrees Celsius. Okay, so now, so let's say this is minus 5 degrees Celsius. Okay. Now, so you have snow, and so you have snow on the ground and stuff. And when you go stand on a ski, okay, when you stand on a ski, what you've done is your weight, this is atmospheric pressure, your weight has been added, and so the pressure has increased on this ice. The pressure has increased to this point, and now it's in the water phase, so this is water. And all this snow underneath you melted, and the melted water acts like grease, and you're able to ski. Okay. So thanks to this negative slope, you're able to ski and so on. Okay. All right. Anyway, phase diagrams are extremely important, and you can find all kinds of phase diagrams for all materials, and material scientists study these phase diagrams and so on. Okay. All right, so the triple point of water is, you saw that this was the triple point of water at the temperature and pressure where all three phases of water coexist. So there's the triple point of water, and it occurs at 273.16 Kelvin and 611 pascals, so 6,000th of an atmosphere. At this point, it's possible to change all of the substance to any phase by making infinitesimal changes to temperature and pressure. So you see, you can go to any phase from the triple point. Okay, so here are the three commonly used temperature scales: Celsius, Fahrenheit, and Kelvin scales. These formulas show you how to convert Celsius to Fahrenheit and Celsius to Kelvin scale. So between these two formulas, you can convert from any temperature scale to any other temperature scale. Okay, and here's an easy way to remember this. So this is approximately 2. So to convert from Celsius to Fahrenheit, so if you have 25 degrees Celsius, 25 times 2 is 50, 50 plus 30 is 80. Okay, so that's an easy conversion. That's a rough, easy conversion. Okay. And Celsius to Kelvin scale, all you do is add 273 to it. All right, so here are some temperatures that we've measured and we've seen. So helium becomes liquid at 4.2 degree Kelvin. Water freezes at 100 degrees Celsius, or at 0 degrees Celsius, 273 degree Kelvin. The surface temperature of the sun is about 6,000 degree Kelvin, 5,800 degree Kelvin. The interior of the sun is 15 million degrees Kelvin. At the center of a hydrogen bomb exploding is about 100 million Kelvin. Okay, so those are some of the temperatures we measure. And here's how you measure these temperatures. Okay, so okay, every body, every object emits electromagnetic radiation. So every object emits electromagnetic radiation. What this is showing is the intensity of the radiation at various wavelengths. Okay, and so this is okay, so there's the temperature. So as I said, the sun's temperature is about 6,000 degree Kelvin. Okay, that's the surface temperature. And what that tells you is, for this wavelength, that is the intensity emitted. For this wavelength, that's the intensity emitted. For this wavelength, that is the intensity emitted, the red graph. Okay. So here's the thing to notice about this. So watch the temperature as I move the scale up and down. So for every temperature, this graph is unique. Okay. So if you take a solid object or a liquid object, this graph, the intensity versus wavelength, the spectral density is unique. It depends on the temperature of the object. So if you want to measure the temperature of some object that is remote, so if you want to measure the temperature, surface temperature of the sun, all you do is, for various wavelengths, you measure the intensity of light coming, and that'll give you the temperature. Okay, so that's how the temperature of all these objects are measured. So if you wanted to measure the temperature at the center of the hydrogen bomb explosion, you measure the intensity of radiation coming from various wavelengths, and you can calculate the temperature. Okay. All right. So here are some of the scales, phenomena we have studied at various temperatures. So, or achieved. We've achieved 10 to the minus 10 degree Kelvin. So that's how close to absolute zero we've gotten. Our body temperatures are 37 degrees Celsius, okay, about 310 degree Kelvin. and we are a very sensitive thermodynamic system. If our body temperature changes by 1%, we feel sick. Okay? So we live in a very small temperature window. Okay? The hottest we've achieved is heavy ion collisions. That's relativistic heavy ion collisions, and we've achieved where they collide. We've achieved temperatures of 1,000,000,000 degree Kelvin. Okay. And so on. Fusion reactions happen at about 100 million degree Kelvin, and so on. Okay, so this shows you various phenomena that we have studied at various temperatures. All right, I'm going to pause now. If you guys have any questions, ask me now.